Hello, this is Dr. Christy Patton-Lokes, a chemical engineering professor at Missouri S&T. We are continuing our study of Chapter 4 on entropy, and we are going to be using our definitions that we have developed in this chapter to define a polytropic process. So let's begin by generalizing the example we had last video, which was a reversible adiabatic ideal gas system that had constant specific heats. And what we saw was T2 over T1 to the C sub P power could be set equal to P1 over P2 to the R power by assuming that delta S is equal to 0 with constant specific heats. Now we also know that we have C sub P is equal to C sub V plus R, and we can define gamma is C sub P over C sub V, simply a ratio of those two. For air, this value is 1.4, and it typically is in the vicinity of that value there. If I do this, remember I could rearrange this so I had R over C sub P or C sub P over R. Let's do this as C sub P over R is going to be, well, lots of different ways I can do this, but I want to introduce gamma in here. So I'm going to divide numerator and denominator by C sub V. And R I'm going to define as C sub P minus C sub V. If I now introduce gamma, this is gamma over gamma minus 1. Now, I can use this, therefore, so that if I rearrange this to the form we actually used earlier, P2 over P1 is T2 over T1 to the gamma over gamma minus 1 power. Or if I start with the C sub V expression, C sub V log of T2 over T1 plus R ln of V2 over V1, I end up with T2 over T1 is V1 over V2 to the R over C sub V. And in terms of gamma, this is V1 over V2 to the gamma minus 1. Clearly you could rearrange any of these things, right, so that you could have T2 over T1 is P2 over P1 to the gamma minus 1 over gamma power, right, just the reciprocal. You could play all sorts of games with this, but these relationships here are an important set of equations that help us do quick calculations for ideal gases. We can kind of summarize this, that T2 over T1 is equal to V1 over V2 to the gamma minus 1 power, which is equal to P2 over P1 to the gamma minus 1 over gamma power. So, when is this true? The answer, technically, is never. Okay, this is never actually true. However, it's such an easy calculation, and the other techniques are going to require us to do some complex integration of long, ugly polynomials, lots of risk of making numerical mistakes. And so what this does is it gives us a way to do quick calculations to check our computer code and make sure that we have almost the right answer, okay? So a lot of the things we learn to do that are shortcuts like this are actually very useful to us when we are trying to verify answers done by computer simulations, etc. Let's now use this concept to do expansion and contraction work of a polytropic process. Now, expansion and contraction work, these are those cases where I have a closed system. And in that case, the reversible work is equal to the negative integral of P dV from V1 to V2. Okay? A polytropic process, if you don't recall, is PV to the n power is a constant. And I'm going to call it K for constant. Okay, nothing special about that K. It doesn't have any real meaning. Now, the reason that's useful, though, is because now then I can make that replacement as P is equal to V to the negative n power times K. Right? And this now, K is constant, so I can bring it out. I forgot my negative sign. There it is. Okay, so this is V to the negative n power dV. And so therefore, I'm going to add 1, right, to the numerator. So minus K, V to the negative n plus 1, and then divide by negative n plus 1, and evaluate that from V1 to V2. This tells me that the reversible work is negative K, V2 to the 1 minus n power, plus K, V1 to the 1 minus n power, all over 1 minus n. We can play with the signs lots of different ways there. All right, now, here's the trick. In some cases, K is equal to P1 V1 to the nth power. In other cases, K could be equal to P2 V2 to the nth power, right? They're all the same. And so I'm going to selectively substitute in P2 V2 to the n power and P1 V1 to the n power. Now, if I add my exponents, n plus 1 minus n just gives me the first power. And so I end up with the reversible work for a polytropic process is going to be, okay, I've got a lot of negatives. I'm going to switch my signs on the numerator and denominator. I'm going to just switch all of them. That's fair. Okay, so this is going to be P2 V2 minus P1 V1 all over n minus 1. Now there's only one problem, and that is what happens when n is equal to 1. Okay, in that case, then, well, that means PV equals K, and therefore, okay, so P is equal to K over V dV, and K is a constant, and so negative K integral of dV over V is the natural log of V. Which is negative PV ln of V2 over V1. Okay, so that's that special case. Now, so again, the question is, when on earth would you ever have a polytropic process? This is nonsense, right? Well, let's consider some special cases. First of all, if you have an isobaric process, constant pressure, well then that implies that n is equal to 0, right? P equals a constant. If you have an isothermal problem, that's actually the same as n equal 1. PV equals RT, correct? And so therefore, if it's isothermal, PV equals a constant. But here's the interesting thing. We just did this one, reversible and adiabatic, or isothermal, or isentropic. N is equal to gamma C sub P over C sub V. And that's actually a fairly broad class of problems that can apply to. So now, what about work in reversible flow? In this case, we are talking about steady flow with a single stream in and out. And if you go through and write out your expression, reversible work is the integral of V dP for the flow in and out, that difference. I want you to go through and do this one on your own. K, again, is P1 V1 to the n power or P2 V2 to the n power, either way, okay? And can you, from that, develop an expression that's going to look an awful lot like what we just had for our closed system? If it doesn't look a lot like that, you're not quite finished. Now, the good news is they have the answer in the textbook, so you'll find the answer, but I do want you to struggle with the math on your own independently. All right, so that wraps up this video lesson. We're almost through with entropy, so I'll see you in one more video lesson. Thanks very much for your time.